Hello my dear children, once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had discussed some of the applications of the PN junction diode. We discussed its application as a rectifier. Today we will discuss the application of PN junction diode as a special purpose junction diodes. So let's discuss about that. Let's get started with today's session. So the first one in that category is photodiode. So here we can just go for a quick introduction. Special purpose PN junction diode. Optoelectronic junction devices. We are discussing more about optoelectronic junction devices. The semiconductor diodes in which the current carriers are generated by the photons is called optoelectronic devices. We had already studied that in a PN junction diode, current carriers are generated. Okay, so in the semiconductor diode in which the current carriers are generated by the photons, not by the external voltage. If the current carriers are generated by the photons or light, photons means light, is called optoelectronic devices. And some of the optoelectronic junction devices are photodiode, light emitting diode. Light emitting diode means LEDs, and solar cell. So first let's discuss about photodiode. So what do you mean by photodiode? What is the application of photodiode? Photodiodes are used for detecting optical signal, or they act as photodetectors. Okay, so they are used to detect optical signal. And this photodiode is a special purpose junction diode. It is made up of photosensitive semiconducting material. So what do you mean by photosensitive semiconducting material? Photosensitive means that material is sensitive to light. Whenever light falls on it, quickly current carriers are generated. And what is the structure? See, here you can see the structure of a photodiode or diagram of a photodiode. It consists of a transparent window, and that window is fixed there so as to allow the light to fall on the diode. And the most important thing is that this diode, photodiode, operates under reverse bias. It's very, very important. So this photodiode operates under reverse bias. Okay, so when light off, energy E is equal to h nu greater than the energy gap. That means you know the energy of the light is h nu. Energy of a photon is h nu. So when the light incident on this photodiode has an energy greater than the energy gap Eg. Okay, and one such a photon having energy greater than the energy gap falls on the photodiode, electron-hole pairs are generated. Okay, electron-hole pairs means carriers are generated, because when we supply light energy, electrons will jump from valence band to conduction band. And whenever electrons jump from valence band to conduction band, holes are generated. So electrons and holes, electron-hole pairs will generate. Now, these electron-hole pairs will generate near the depletion region. Why? Because window is near the depletion region. So this is window. This is the transparent window, and it is located near the depletion region. Hence, electron-hole pairs will generate near the depletion region. And this region has electric field. You know, depletion region has electric field. Under this electric field, electrons and holes will drift. That also, you know, we had studied this concept in the previous sessions. So this electric field established within the depletion region causes the electrons and holes within the depletion region to drift. Okay, so electrons flow opposite to electric field. That means towards the n side. So electrons will flow towards the n side and holes will flow towards the p side. Holes will flow towards the p side. Okay, then as a result, the n side will get more and more electrons and p side will get more and more holes. So n side gets more and more electrons means n side will become more and more negative, and if p side gets more and more holes, then p side will become more and more positive. Okay, thus a potential difference is generated between both ends of the photodiode. One end is becoming more and more negative and other end is becoming more and more positive, and due to this EMF a current flows through the photodiode, and this is known as the photocurrent. So this current is known as the photocurrent, and the potential difference developed is known as photovoltage. Okay, so this is about the working of photodiode. Okay, now we need to discuss the VI characteristics of this photodiode. VI characteristics is also very important, and you should study the VI characteristics of all the special purpose junction diodes. So here in the photodiode, how does it work? It works when light falls on it. When lights or photons falls on it, what happens? Electron hole pairs will be generated near the depletion region, and these electrons and holes will drift to the respective region. That means electrons will drift towards N side and holes will drift towards P side, and as a result N side will become more and more negative, P side will become more and more positive, and due to which a potential difference is developed across both ends of the photodiode, and hence a photocurrent will flow through the photodiode, and this potential difference developed is known as photovoltage. And the most important thing is that photodiode works under reverse biased condition, and also this electron hole pairs are not generated for all the light incident on it. Only when the light incident on the diode has energy greater than the energy gap of this semiconductor material, only such light can generate the electron hole pairs. Now let's discuss the characteristics. Characteristics means graph, VI graph of a photodiode. And I told you photodiode works under reverse biased condition. So the graph of photodiode can be observed under reverse biased area. Okay, so here you can see, we had already seen this graph in our dual nature of radiation and matter when we discussed the photoelectric effect. So here you can see the photocurrent increases with intensity. Okay, photocurrent increases with intensity, isn't it? Here for I1 intensity, which is the less intensity, this is the value of photocurrent, right? And when the intensity increased to I2, again the value of photocurrent increased. Again when the intensity increased to I3, the value of photocurrent also increased. Like this, see here the photocurrent has increased. Then again when the intensity increased to I4, the value of photocurrent, again maximum value of photocurrent also increased. So what is the peculiarity of this photocurrent? Photocurrent increases with the intensity of light. Also, photocurrent increases with the reverse bias voltage initially and then attains a saturation value. So here you can see, initially when the voltage increases, so this is the voltage axis. So initially when the voltage increases, current also increases like this, and finally they attain a constant value. So this is the constant region. Here the photocurrent doesn't change even if the voltage changes. So voltage is increasing but photocurrent is not increasing. Photocurrent takes a constant value, that means a saturated value. So this is the saturation region, but initially photocurrent increases with respect to voltage. Okay, so this is the VI characteristics of a photodiode, just like what we had discussed in our dual nature of radiation and matter. Next, we can discuss about light emitting diode. That is the second category in a special purpose junction diode. So what is the application? They convert electrical energy to light. So LED is a device which converts electrical energy to light, and it consists of a heavily doped PN junction diode under which the forward bias emits spontaneous radiation. That means this diode LED operates under forward bias condition. Photodiode operates under reverse bias condition. LED operates under forward bias condition. Here, On the screen you can see a diagram which I have drawn. It is a p-n junction diode, and here you can see the p-type semiconductor. Holes are the majority carriers, which is represented by that purple ink, and here you can see the n-type semiconductor, and electrons are the majority carriers in the n-type semiconductor. This is the depletion layer. Near the depletion layer or within the depletion layer, minority carriers are present. Minority carriers are denoted by the blue color. Okay, so electrons and holes, which are the minority carriers in the respective regions, are represented by the blue color. Now, this diode is in the forward biased mode. See, positive of the battery is connected to the p-type and negative of the battery is connected to the n side. So this p-n junction diode is in a forward biased mode, and under forward biasing what happens? The positive of the battery repels the positively charged holes towards the depletion region. Similarly, the negative of the battery repels the negatively charged electrons towards the depletion region. So what happens? This holes enter into the depletion region and combines with the electrons present in the depletion region. Similarly, here electrons enter into the depletion region and combine with the holes within the depletion region. So in both ways, electron-hole recombination occurs, isn't it? Electron-hole recombination occurs, and during this recombination of electrons and holes, energy is released in the form of photons, and some photons may have energy less than the energy gap. Some photons may have energy greater than the energy gap. So, those photons having energy less than or equal to the energy gap will be emitted as light energy. At the same time, those photons having energy greater than the energy gap will move to the conduction band and contributes to the conduction. Okay, so during electron-hole recombination, photons are emitted. Energy is released in the form of photons actually, and those photons having energy less than or equal to energy gap are emitted as light energy. At the same time, those photons having energy greater than the energy gap moves to the conduction band and contributes to the conduction. Okay, so that's about the working of light emitting diode. And what is the VI characteristics? VI characteristics is just like our p-n junction diode. Here you can see the forward biased mode. Here you can see the reverse biased mode, like that. Okay, but there are some advantages for this LED. So let's discuss about the advantages of LED. LEDs have the following advantages over the conventional lamps: low operational voltage and less power, fast action and no warm-up time required, long life, fast on-off switching capacity. No need to explain all these points. You are very familiar with all these advantages of LEDs. Now, let's discuss the last category of special purpose p-n junction diode, that is solar cell. And you all are aware of the use or purpose of solar cell. Solar cell helps to convert solar energy to electrical energy. What is the principle? Solar cell are the photovoltaic devices which convert the optical radiation into electricity. Optical radiation, that means the sunlight, is converted into electricity. Okay, so this figure gives us the construction of the solar cell, and using this diagram we can explain the working of the solar cell. Okay, now so here whenever light falls on the top surface of the solar cell, this is a solar cell and it is made of silicon or germanium. So whenever the sunlight falls on the top surface, electron hole pairs are generated. And also one more thing, electron hole pairs are not generated for all the photons falling on the surface. Electron hole pairs are generated only for those photons having energy greater than the energy gap. So if the energy of the photons falling on the surface has energy greater than the energy gap, those photons will generate the electron hole pairs, and these electron hole pairs move to the respective regions under the influence of the electric field within the depletion layer. So as a result, the electrons start to flow through to the N region, and holes start to flow to the P region. Okay, so more and more electrons are accumulated in the N region, and more holes are accumulated in the P region. So as a result, what happens? See, when more and more electrons are accumulated in the N region, this N region will become negative, more and more negative. Similarly, when more and more holes are accumulated in the P region, this P region will become more and more positive. So a potential difference is developed between N region and the P region, due to which the a photo current starts to flow across the diode. Okay, so here the top surface is made of N region, and the back contact is made of the back surface is made of the P type. Okay, so a potential difference is developed between the P side and N side, due to which current starts to flow through the diode, and this current is the photo current, and the potential difference developed is called the photo voltage. So the working is similar to that of a photodiode. So that's about the working of solar cell. Now this graph is very important, and you should know to recognize graph. They will ask you the graph, that means they will ask you a question like this. This graph represents the VI characteristics of a special purpose junction diode. Name that diode. Okay, so which is that diode? It is a solar cell. And what is the peculiarity of the graph? Here you can see this is the open circuit voltage, and this is the short circuit current, because we are not providing any voltage to the solar cell in order to generate the electron hole pairs. Electron hole pairs are generated by the sunlight falling on that solar cell. So no voltage source is used, but still voltage is there and current flows, isn't it? In the absence of external voltage source, still a photo voltage is established there and a current flows there. So such type of voltage and current is known as open circuit voltage, and this open circuit voltage gives rise to short circuit current, and this is the VI characteristics of open circuit voltage and short circuit current. And not all materials are suitable for fabricating solar cell. So what are the criteria for this material selection of for a solar cell? So the band gap should be between 1 and 1.8 electron volt. That means the energy gap between the valence band and conduction band should be nearly between 1 and 1.8 electron volt. The material should have high optical absorption. Electrical conductivity of the material must be high. Availability of raw material. The material should be available, easily available, and it should be cost effective. So these are some of the criteria for material selection of a solar cell. So that's all about the special purpose junction diodes. With this, I am concluding this chapter. Notes of the topic and YouTube video have been uploaded. Just go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.